in such a way that the sum of all the weight of edges in that tree is minimum. So we call it minimum spanning tree. It means we would try to find the let's say somehow the best way to link all of the knots together. In real life, that could be helpful. Say if you link all of the, say you have many machines in one building and you want to somehow link them together using the cable. You want to find out the best way to do it. Or in the real life, we have many say many location, and then you want to link them together. So we can find out this one, organize so representing in a graph and then link them together. They one of the thing. Now so we minimum spanning tree. Last time, as you remember, that we have the problems here, and then we had the solution. The crucial algorithms, the way is quite trivial. It's like quite normal. Is we just sort all the edges in the increasing order, okay, and then we try to take the smallest edge first, one by one, until we can link all of them together. Just one thing is that the key thing is we have to take the edge that will not form a circle in our graph. That is the thing. So that in order to solve it, last time we just remember you had the way. It means every time we link two vertices together, we just rename the vertex like the two vertices to the smallest number, so that next time, every time we take an edge, if the two extremity of that edge have the same ID or same number, we know that they are in the same, like the set we are using, and that will form a circle. Okay, that is the first way. Okay, now so here these are the algorithms. You see, we give number to each vertices to each vertex, and then if they are the same, the link would change the number. So here people try to analyze the complexities. So you see, we have the sorting algorithms, maybe the best one. We can try, that could be with sort, quick sort, and we end up n. So we have compared to extremity. So we have n step, and to renumber vertices, it takes time. Okay, because we have, every time we do, in the worst case, we have to renumber every edge once. So that roughly n square. That is one algorithm, and you see this is not really a good one somehow. Okay. So people now can come up with another solution. Okay, so the solution is just very close to what we see in the cursor. So Brim algorithm. So here again we try to we have vertices. Okay, so we have vertices here. We try to here P is the weight of x and y. Okay, so we have two things. First on, we have the number of the set here. We have A is a vertex, so it means every time we take an edge, we will put this vertex x into the set. Okay, and we increase it one by one. Now let's try to see this one. I will show you an example in OneNote. Okay. So not this one. Just 1 second. I would need to move it here. Okay. So it should be like this. Drawing. Okay. Yeah, whatever. So here, that's it. So we have up. time, and so okay, whatever. So we have this one up, and then we have this. We don't have actually this one, and then we have this. Okay, let's say we have so 2, 3, and 4. Okay, and we may have this one maybe. Wow. Something like that. Now, so no, it's not good. Okay, let's say this one. So now the algorithm as I say, hey, at the beginning, try to set everything is empty. We put the setup market vertex. We start from one given node. So we start from here. Let's say we start from one vertex. Okay, and then we put it in sorry, at the mark set. Okay. Next step, what we try to do, we try to expand from that node. Okay. Now what we do up here, they say try to take. I try to put it. Okay. Okay. So say why this we don't have enough edges, then we take we for each xy, okay, we name it u, in such a way that the edge starting from the mark set here, our set at the beginning we have one edge. Now from this edge we can go into two ways, this one, and for all of the edges like that, starting from this one and go to another, we take this one with the minimum value. This means in here we have two eigen edges from the set, so we have 2 and 3, so we take 2. Okay, so we take 2 and we put it here. Okay, so we have this one. We include the y, it means the extreme of the edge to a, and we include this edge into the outer set. Okay, and continue. Let's say I have this. Assume we have this one, this one. We have 1 here. We have say 10 here. Okay, we have 4 here. Say. Okay. Now you see we have this one. We start from the one node. We reach the second one. And then now what we do is we repeat this step. So for all the edges that have x in A in market and y is not in A, it means the others, it means we are considering the node that are going out of the mark set. So it go now. Make sure that we will not have any circle, because every time we go out. Okay, do you agree? So every time you go out, you go out. So you will never have the situation that we make a loop, because we are going out. Okay. So that is the idea. So this time, so we have 1, 2, 3 edges that going out of the set. So the smallest will be this number. We put it 3. So we take it. Okay. So we take 3. So we have this. And next time, so what we have, so this edge 4 is between two edges, 2 vertices in the set, in the mark set. So we will not consider it anymore. So we consider 10 and 1. So 1 we consider it. We take it here. Okay, so we take it. Okay, and then this one we have 10 and 4. So we take 4. We take this one by using this edge. Okay, everyone, is it clear for you? So now what I want you to do is try to do it with this one. Okay. Assume that we have this edge. make it here. Where is it? How can I do it? Okay, put here. Get bigger. Now, so everyone, so please do it. Okay. So try to find the minimum spanning tree of this graph. Okay. Is there algorithms for you? This one. Everyone, please try to do it. Yeah, you can say the grading algorithms. Okay. It's yeah, both algorithms is ready. The threshold is greedy in another way. It means greedy in threshold is it takes greedy means they will take the smallest value first. Okay. It means we take the smallest one. This one is kind of the same.
Teacher, your mic is mute.
I'm sorry, can you hear it now?
Yes.
Thank you. Yeah. So do you need do you need to repeat everything? Or is it okay? Just continue, huh? Okay.
Yeah, it's fine.
Yeah. So now continue with that. So with what we have this one is this one. Sorry, where is it? Okay. So now here, our matrix will be 11, 12, 13, 8, 6, 4, 10. Okay, I will take 4. Okay. Okay. Now what we have, our win will be 12, 11, 10, 9, without 6. Okay, because 6, 2 edges here are in the set already. We will skip it. Okay, 8, 13. So what we do, we will take 9. Okay, and sorry, it's not 9, it should be 8. No, it should be 8. 8 is the smallest one here. Okay, clear? Okay, so then next time 9. Okay, next time we 1. Okay, next time will be 11. So that's it. So do you have the same result? Hello? Yes? Okay, great. So Hiếu, is it okay now? Do you need me to repeat it? Võ Minh Hiếu, is it okay? From the beginning, okay, no problems. Okay, so here, okay. So everyone, if you have problems, just ask me to do. Okay, don't worry. I have one here, so I can repeat, undo and redo easily. Thanks for. Fortunately, now at the beginning, this algorithm we can start from whatever I want. I just pick one note. I pick the first one. Okay, from the first one I put it in market. I mark it, and then I will take the outgoing edges. That outgoing edge in this case means the edge that go out of the set. Here is in the slide here. They say take the edge xy in such a way that x belongs to A. It means x is a member of A and y is not in A. Okay, so we have here, I do it. So I up. Okay, it's okay. Now, so I take 7. I'm going now. So I take that edge. I mark the termination. I mark this one. Okay. Then I continue. I continue with the smallest one. So smallest one will be 3. Okay, among 12, 13, 6, we have 3 is the smallest edge that go out of the set. Okay, this one. So I take it. So I have mark. From that mark, I check again. My list of outgoing edges changed. Okay, now we have the others edges and one edge 2. Okay, there are 2 of the way 2. So I take it here. So now I extend it. So I have more outgoing edges. So it will be A 5. See 5 here. 5. And 5 is smallest. So I take it. Okay. Take it. And now from 5, I have new edges. The smallest one will be 4. Okay. I go. Put it here. Okay. Now again, take it. 8 is smallest. Take 8, 9, 10, and 1. After I take 9, I have the 1, and then from 1 I take 11, and that's it. Okay. Get it? Is it clear, everyone? Now move forward. Okay. Yeah. Okay. Now these are primordials. Now there's one thing that usually later on when you work with a like we do a bit of research, if you really want to go that direction, there's one thing that people have to do in all of the case when you propose a new solution is that we have to prove that our algorithms work. Okay. Now so think about that. First of all, do you know how to prove by induction? Can someone tell me what is proving by induction? Everyone, do you remember what is in math in our university? Did you learn about proving by induction or something like that? Did you have chance to learn about that? Everyone, someone tell me. Hello. So in math, you didn't do any proving? Say the format is normally that will be like this one. They say is prove by induction on the number of steps, means so they say they will that it's just like the proof, the structure of the proof will be like that. So consider when the number of steps is 1. So now let's say we trivial. So step number 2, induction. Say assume that somehow now I'm trying now. Assume that the number of steps is n. Okay, and we it means the step is n in our algorithms. Okay, we are reaching step number n, and that step, all the edges in S are valid, and are parts of the span tree. Okay, and then we prove that if we do step n plus 1, okay, so we set all the edges in S are also valid and are the part of the minimum span tree. That's what we do. So that's what we're proving. Okay. So remember, in Vietnamese they say that is quy nạp, no? I remember the name. So that is part of the work that we have to do if we somehow say try to propose some algorithms, some new way to do things. So we have to prove, and induction is one of the both way to do it. Okay, so here the idea is just say, hey, every time I take one new edge, that new edge is valid and it is the best solution or the best option I can take. So that, and if I continuously to take the best option, it is ready, then when we terminate, when we finish, we terminate the algorithm. When we finish, we will have the minimum span tree. Means on the edges there will be the smallest edge, and that set of edges will form a tree. Okay, so I will not go into detail because it's just an idea. It will take you some time to think about that, but at least what I want to mention here is that we have that kind of thing. Okay, when we do a bit of research, maybe, so that will be like this. Okay, on the computer science research, so people have to come up with new idea. You propose some way to do things, but if you do research, we must prove it that is true. Okay, so that people can follow. So because when you look at algorithms like that, people say, hey, let's do that. So it's not easy for the communities or the researcher to accept that your new algorithms is valid. Okay, so we must prove it. Okay, that is the thing. Now we for Bremer algorithms here, people say one way to do it again is we can use a priority queue. I mean, every time we set it up the edges and the thing, and we just say put it in the queue, and every time we take the minimum value from the queue so that we have it. Okay, yeah, that is the thing. Now, this one I will you can read it at home. So because we want to move to another thing. Okay. So now for the complexities in general, if we implement it using heap and the queue, priority queue can be implemented by a heap. So what we have is the complexities in total that would be m log n, m in number of edges, n in number of vertices. Okay, so it's quite good in terms of performance. It's better than the others. Crucial algorithms, when we have to renumber the value, that would be n squared plus n log m. Okay, so now we are moving to these algorithms. This is one of the basic operations that people do with the graph. That would be finding the shortest path in a graph. Okay, it has many applications of this kind of thing. So we represent the map in Google Map, maybe in Ho Chi Minh City, and we will find the path. We had the plan. We want to find out the way to do on the job in the best, fastest way. We have many such a thing. So, but in shortcut path, we have some definition that we should care. Now again, we are change the context. We want to work with directed graph. It means the graph have the direction. Okay, and we have the weight function. Okay, so say W is a weight function. Okay, and then we have this thing. Now there is one thing in the finding shortcut path algorithms that we must aware is this one. This is very important. It is the absorbing circuit. Absorbing circuit. Where is it? It is circuit. It means it close. We start from one node and we reach. We go through many nodes and we go back to that node again. So it forms a circuit. Okay. But in the weighted graph, here the weight function, it could be anything. The weight function map the edge to a real number. So it could be a negative number. Okay. So now, if it is negative, what could happen is we may have this one, absorbent circuits. Then we have this one. If we have this one, say we have many nodes in the middle, but the sum of the weight, the sum of the weight for all of edges here, if it is negative, means that we always can find the better path into weight if we take this circuit many times. Okay, so say we have here 5, okay, and the sum of this one is -1. Okay, and this is 10. Okay, so we're going to say 5, we go this loop, 1 plus 1, we have -1, we have 4 plus 10, we have 14. So if we will say, hey, I'll do it again and again and again, so we have smaller and smaller. Okay, so in such a case, normally we cannot find the shortcut path. Okay, because it's negative, we cannot find it. Okay, so we should not, when we work with the graph, we should check whether or not we have, say, absorbent circuits or not. If yes, we cannot do anything with it. Okay, so there's the shortcut path. Okay, now all the algorithms they will say if they have no absorbing circuits, then we work with shortcut paths. Okay. In the shortcut path algorithms, we have two kinds of algorithms. The first one, we call it single shortcut path algorithms. This is the algorithm that have us to find the path from one node to all the other vertices in the graph. Okay, so we call it single source shorted path algorithms. Okay, here these algorithms, in order to avoid the absorbing circuits, they say, hey, if the way are non-negative, use my algorithms. Otherwise, please skip it. I don't want to handle negative number. Okay, so if you have negative number, you cannot use this algorithms. Okay, that is the constraint, the assumption the make. Now the idea is just very close to the algorithms we had mentioned. So this algorithm, I think that you learn about that in discrete math or something. No? So we start from vertex S, okay, and we build a set of edges by taking the successive edges with initial vertex in D, and then the other extremity is not in D. Just take it. Just very close to what we have from algorithms. Okay, when people write down as the algorithms, that will be like this one. So we have this one, and let's check it. So we have here we have the set D. Okay, at the beginning, this single source, we have to start with one node. S is source. Okay, we have A. Let's check the meaning later on. AM is nothing. S is x1, the first x. The distance from S to S is 0. Okay, K step is 1. For all of the edge, so all the vertex, okay, different from S, we set the distance from S to that vertex is infinity. Okay, it means we cannot reach it. Okay. So why this one is smaller than K, and is the xk, we check it. What is it? Is smaller than this number? We do something. So for each edge, okay, such a way that the initial of that edge is xk, k1, x1 is s, yeah, as the beginning, okay, and the terminal of u are not in the D, the set of edges, vertices that we take. So we say, then we do it x, the terminal of u is x. Okay, put it x, and we compare. If the distance from S to X is bigger than the distance from D to XK, XK this one is the initial, plus the weight of the edge, then we update it. So we have here the ancestor of X will be U. So mean, say the edge that happens to reach X will be U. Okay, that is the meaning. Okay, so after we finish with the for loop here, we will select the S out of D, X out of D in such a way that the value of the distance of X is minimum. Okay, among all of the vertices out of U, so we use it at the next value to consider. Okay, so do you remember the algorithms from discrete math? Now, eliminate. Okay, so try to find out the example. a little bit. Okay, shortest items, shortest that. Take one graph for shortest bus. But that I have a style when I have all the example here. Where's my file? Sorry, one second. Okay, maybe this one. Okay, here, let's say I will make this like this. I'll take this figure. Okay, put it here. Where is it? Up. Where is mine? Okay. So here the graph. Okay. So we have one graph. It's a bit complex. We don't care. What we want to find the shortest bus. Let's say starting from A. Okay. Now let's build me. Let's try to do it. Okay. Where's my 1 second? There's something wrong with computer. Okay. Now what we want to apply the algorithms. Okay. Now we start from A. Okay. Right. Okay. Now, so we will do it here. Okay. So we start from A up. Okay. So what we do, we try to use this algorithm. Okay. So at the beginning we set A. Okay, is 0 equal to the source. Okay. And here for all of the vertex in V and it's not S, put it infinity. Let's say everything is infinity here. Okay. Now so we try to increase k by 1. So at the beginning we said k is 1. Okay. And x1 we set it to S. Okay. So we start from A. Now for each S that have initial S is D. Okay, say we have this, we mark it like this one. So here, or I say for each S here, initial is xk. Okay, in this case A, and the terminal is outside of the max 1, so we take it. Okay, so here we have two arguments. A, the outside of the market will be B and D. Okay, so we take one of them. And now we try to set it to X, and say if the distance from S, from the source to X is bigger than the distance of xk plus the edge, means that say he has 0 here and the distance at beginning here is infinity. Okay, it is bigger than anything. So if they say if the distance So D 0 plus 1 is smaller than this, we will update. Okay, so what we update, we set the distance to that knot equals this plus the edge. So this one we set it to 1. Okay, because we found a new edge, a new path from the source to this knot. So here we set it to 3. Okay, and what we do, say then we select the S is not in D in such a way that the distance from source to that is the minimum of all the knot outside of the mark, and we check it, put it in D. So outside here, everything else are infinities, and this one we have the smallest is D of D, so we take it. Then you see again a ready algorithms, we take it. Okay, see our set. Now, so we have this step, we take it and we put it 1. Okay, and we will use that knot. Okay, so X here, then we put X XK and we will repeat this one. So this one we update again. From here, from 1, what we can go out, go to C, go to E, and C infinity we make it 2. Okay, this one we make it 5. Okay, then after we update, we find the best value outside of the mark set, so it will be 3. Oh, sorry, it will be this one, 2. The smallest, we take it. Okay, and it is smallest, and then from this one we update. From this we have 1 and only one thing to do. Okay, and from outside, this is the smallest, so we take it. Okay. Okay. And from this one, we update the outgoing. Oh, sorry, I'm sorry, I make a mistake somewhere. It's the sorry. So sorry. This one, it should be 3. Up. 3. The distance from the source is mean the distance of 1 plus the weight. Okay, and this one is 1 plus 5 is 6 for E. Okay, sorry. So we have here the best one will be C or D. In this case, let's say continue. I will take this one. Okay, from here we take it. Try to update. From here we have 3 plus 1 is 4. Okay, and among the best option, we take this one, E3. Okay, because we sum. So from 3, we try to update. From 3, go to edge, D3, so here we have 5. Okay, and from 5, so now we check the whole map outside. So we have 4. Okay, so we take it. So from 4 we go to here, so we have 6. Okay, so now consider all edges here. So we have this one, 5 is smallest. Take it. Okay, and here we update. Now in the first time we had a function. So we from H, we can go out to F. So the distance, if we go this way, so it up here we 5 plus 4 is 9, and it is bigger than the current value of F. Oh, sorry, but F is outside. We will not care about that one. This one, we we take it already, so we don't care. So this one H, we go to G. G, we have 5 plus 5, 10, is bigger than infinitive. Sorry. So we have this. So we have 10. Okay. And for all of the net, like this one, well, we try to take the smallest one, maybe this one. So we take this. Okay. So we have 6. But on the edge go out of E, we are the smallest already. Or take it already, so we don't check it anymore. So we have here 6, and then next time we take this one. So it's 6 and update, nothing to update for this one. And finally we have take G, 10. So that is the result. So the value here is the shortest path distance from the socks to the knot. So here 5 means the best way to go from A to H this way, and the value is 5. Okay, this way can go to H, but you see it 1, 5, 6, 1, 5, and 3 is bigger, so it's not a good solution. So this algorithm is like that. So everyone, can you follow my instruction? Is it clear for you? Hmm? Now it's time to play with an algorithm, so with a value. Okay, so I try to say, how can I make it a little bit hard? Yeah, maybe it's hard. I don't know. Okay, I will try to use the same graph after I change the number. Okay, so that we may have to see something new. Okay. Okay, so everyone, so I will use this one, the graph again, but with different number. Just try to play with that, okay? Okay, so again, starting from A, I want you to try to apply the algorithms. This algorithm, of course, there's many ways to present it, but at first we try to run it in the graph directly. So here from A, so we set initially we set this 0 and everything else is infinitive. Okay. What we do, we take the item in the mark. Okay, then we try to use all of the edge that go out from that K. It's been on the outgoing edges of that in such a way that the terminal is not in the market set. So here, say from A, we can go out to B and D. If B and D are not market yet, so we can use it. Update the value, okay, and continue. So everyone, please, okay. So if you want, you can have small break. to refresh, and then after 10 minutes or so, you go back to and implement the algorithm or run the algorithms. Okay. So let So everyone, please come back and try to run the items. If you finish it already, just tell me, and I may want to quickly go through this one. So here are the list items if people want to write in like to do it in the text format. So we have A, B, C, D, E, F. So what we do is say, hey, at the beginning we set the value, say A0, say B infinity. And this one. And the same for CD. Okay. So we have this one, say the market set. And the second column will be not mark. Okay, and maybe. So for mark at the beginning we have A. So maybe we say so mark it, and then we say I don't know how to do it. No problem. Try to say hey, no, B, C, B infinity. B, B, E, F, E, H, I. So then we can have we take A. So after at the beginning we have nothing here. So we have A0. Okay. So we may need to have one more column. Say, how can I add one more column? Table, insert column. Okay. So select it. Okay. So here we select A0. Okay. So remark set will be A at the beginning. So we set here. We have B is update to. So we have B update to 3. Okay. D the same remaining. The D update to 1. Okay. So from that one, I will select D1. Okay. So we have A and D here. So from D, what we do, we will update H. So we have B3, okay, the same. On the infinitive, yeah, H is what? 6. Okay. And then we select B3. So this is the one if I ask you to do it in the exam. So please follow this kind of format so that you can have something. Okay. I will do it like this one. So here the node that have value, the others have no for infinitive, put it there. So here after we will select B, what we have, we update B, we take B already, so we have C will be 5, no, and then E will be 4, okay, so because we have 3 plus, and then we have H 6, see. So let's say that this is why people say we can use private queue. So then we take E4. We have A, B, D, B, E. So after we take E, we have a C, untouched, H, untouched, and E we are off. Now from E we can have E go to H with E4 plus 1, you have 5. Okay, so 5, so we can update to 5. That is the thing. Okay, we'll update because it's changed. There's one part from A to D to H, that is 6, but now we found a new part from A to B to E to H, it's just 5, so we update. Okay, and the other is the same, unchanged, infinitive. So from that one we can take one of them, we can take C 5 if we want, A, D, A, B, D, D, E, and now C. Okay, so after C what we have, yeah, you can draw it like that. Yeah, it could be like that long, so whatever you want. So so here, so from C we have the F. Okay, F will be 6, okay, and H5 is the same, so we may take X5. So A, D, B, E, C, and H. Okay, so for H we can update F6 the same here, F6 plus 4, no, F, where G 5 plus 1 is 6. Okay, so we take F, A, B, yeah, and then F5, F6, huh? Or F6, yeah. And then what we do, so F we have I is 6, 8, okay. And G, so we take G6, no thing. So we have A, D, B, E, C, H, and G, and then I, A, and then we take I, A, and then finish. Okay, so we have everything. And that's it. Okay. Yeah, of course. Yeah, in this script math in Vietnam, yeah, we can use that kind of thing. So you draw the value, the table like that is still okay. Okay, everyone. So I have that you are now okay with the value, these algorithms. Okay. Now, do you have any question on this? It's quite. I know that you learned from discrete math already. Now, let's back to this one. So this algorithms is like this one. So now what we have, we said the complexities because we have to find the minimum here. like number 10. So we find minimum of outside, so we have to, every time we find minimum and we do it for n time, so the worst case will be, or the complexity roughly will be n squared. Okay. Now we have another algorithm that is very yeah. These algorithms is a bit different. The way the algorithm solve the absorbing circuits is, say we can work if the Reup have no circuits. Say okay, if we have no circuits, we can do whatever we want. Okay. So they are different from these algorithms in the sense that it have no circuits in the Reup, and it means that it also means that it can handle negative edges. Okay, so we have two ways to avoid absorbent circuit. The first approach from Dijkstra, say, hey, I don't want to work with negative number. The second approach from Bellman, say, hey, I can work with negative number as long as I have no negatives, no circuit. Okay. So that is the algorithms, two different ways. Okay, so these algorithms here. So now maybe try to read it because and later on, if some way that you had to read some paper or some some computer science research, maybe this is one you read it. Say Bellman algorithms, we start from the Reup G with the S socks. Okay, we have some D, we don't know it yet, normally a mark. Say A ancestor, S is sock starting the distance from S is 0. Okay, we set everything in the vertex, but not the socks, put it infinitive. It's quite trivial. Now, what we can do, say, try to read it. What does it mean? Y it exists, and X is not in the set here with all of its predecessor in D. What is it? What does it mean by that? Hello everyone. What does it mean by this statement at line number 4? The others? Everyone? So now I will show you this one. Now, first of all, before you run the Bellman algorithms, whatever it say, first of all, we have to make sure that in the graph they have no circuits. So let's say in this graph, they have, is there any circuit? Yes, we have D, H, G, okay, H, F, I, A, B, E, okay. So I changed it a bit. So we have here a graph without circuits. We cannot make circuit. No, sorry, this is circuits. How can I change it? So before we run the payment algorithms, we have to make sure that our graph has no circuits. Okay. So in this case, we have circuits. So I remove it here. So here, so we have do it manually. Okay, no circuits. Now, what we want to run it. So the algorithms, what I say, hey, at the beginning we start with S from D mark set. Okay, say we try to put S to that set and set everything initial. So we say Y there exists an X. Okay, then not in D. It's been one D set of vertices here. Next is not in D. With all the predecessors are in D. Say here these algorithms say at the beginning we say we have this. Okay. Now let's say if there exists a node outside of the D, outside of the mark, but with all of its predecessor in D, it's been all of the incoming edges go to be are in A, are in the mark ring point. So say E is outside of A, but the predecessor of E is been B, E not in D, so we will not consider E. So here H, we have three predecessor D, E, H. D, E, F is not in market set, or so we will not consider it. So actually at the first step, so here B, all of the predecessor on the path that go into B are considered, or on the not are considered already. So we say hey A, okay. So B can be considered, D can be considered. This approach is a bit different from the DSA algorithms. So from the mark set, we take the best not outside of the set, okay, but we don't care about how many paths or how many edges that can help us to go to that point. But now for this Bellman, we say we only consider the node only if all of the paths going to that node, let's say B, starting from the node have been considered already. So in this case, like we try to run and we see, okay. So after we have all the instances in D, what we do, we try to find the min, the smallest U, in such a way that the terminate U X is mean here B. Let's say we take B, and the initial of that in D, it means initial of that in D is in A, the predecessor of B is in A, and the value, the distance of IU, the initial of U used in H. Here, let's say we consider this H. Consider this one, and the initial, the distance of initial plus the weight of here. So initially we have 0, we have 1. So we check this one, we check it mean. Check the mean H. Okay. If that we have the mean, so we can do it. So it means, let's say, assume some way in the graph, in the exploration, we have this one, or we consider. Now from H, okay, we have 3 H come into S, to H. Now we will check, let's say we have number 4 here, assume that we have 4. We have 0 or 2 here, and it is 1 here. Okay. So what we do is, in this step, say we try to find the mean h, where we have 4 plus 2 is 6, 2 plus 3 is 5, 1 plus 4 is 5. So we take the mean of that thing. So that should be e to h or f to h, whatever. But we should take the mean of all the h that go to s to h. So that is this function. Okay, we take the mean. Okay, so we take the mean h. Okay. After we do that, so we say this, the distance to that node x, okay, to the node x, in our case here is h, and equal to the mean of the sum, and we put it as the market set. Okay, so this one, if we say we take this part, let's say, and we take h and put it in the set, that is the situation that may happen. Okay, so the payment, we do it a bit different. Now let's run the payment algorithms together. So say here payment, so this one, okay, now we say, hey, A, we take B, and D is all of the predecessor of them. It means we take one edge, so we have here, we check it, we mark it, and the distance is 1. Okay, the distance here is 3. Okay, so now we see, after we take that, we include x into the market set. So we say we consider B and D. Okay, now all for the next one, where C go out from D, B, so we have this, we mark it like 3. Okay, and this one only one. So can we take H now? No, because their predecessor E and F have not been considered yet. So here we have E. Now go from B. So we take this. Take it. Consider the mean. The mean will be 1 plus 5. We have 6 here. Okay. And now we have this C go to F. So we have 3 plus 1. We have 4. And now, after we consider all of them, now the argument, so we have 2 ways. So we can consider this one first, or this one, whatever we want. So this one, we have this 2. And this one, we have 4 paths that go to H. So 3 plus 2 is 5. This 9. This 8. So we take this one. Okay. So we put it 5. Okay, so there 5, we have 4, and that's it. Okay, everyone. So you see that the way that the Batman algorithms work is a bit more careful than Discra. Discra say, hey, if I have an edge, if it's smallest, I take it. Okay. Now for Batman, they will try to consider the node only when all of the predecessor of that node have been considered. Okay, so here with all of its predecessor and D, so that in that case it can handle negative value. Okay, so that is the Batman algorithms. Is it clear for you, everyone? Do you have any question? Hello. Yeah, for sure. It's hard to read the pseudocode like that, but in I know in research, people try to write like this. Yeah, it's a bit not really close to what we used to do in the coding, but this is formally defined so that people can understand it in the same way. But what I just want to show you here is that we have two different ways, at least here, to compute the socket bar. And again, remember the key thing: we cannot find the socket bars if we have a solving circuit. Okay. The second thing, these algorithms can only run on a graph without negative number. This is one way to avoid a solving circuit. And Bellman algorithms, on the other hand, can run with the negative edges, but the graph should have no circuit. Okay, you get the idea? So if you don't have any other questions, so yeah, now we'll try to finish it. This one. Yeah, in few minutes I will finish this one. Well, okay. So the in shorted bar algorithms, what we have is we try to find the shorted bars. Last time we single socks is mean from one socks node. We try to find the path to all of the reachable node of that socks. But they have another case when people say, I want to find the shortest path for all pair of vertices in the graph. Okay, so it'd be a bit different, because now if you all of these algorithms the n square at the complexity. So if you want to say to run it, so we have to run it n time, so that you can have the all shortest path from all the nodes in the graph. So there is one algorithm that almost solve that. Is they say flow algorithms that try to solve all pair shortest paths. Okay, so here the algorithm is quite say simple somehow in terms of code, but the complexity O(n) square. Okay, or O(n) cube. So so that is the sorting the shortest bar algorithms. So I just mentioned, and then we have many other problems. This one we have flow algorithms in graph theory, and I will not show it. And we have max flow min cut. This problem is very interesting. Say you see that let's say in the network or the traffic in Ho Chi Minh City, okay, they have problems. Say we want to find out what will be the maximum flow. It means the maximum amount of vehicle that can go in the same time from one place to another place, from the source to the destination, using the network, let's say the traffic in Ho Chi Minh City, the road and street in Ho Chi Minh City. So they try to find out the maximum flow. It means if we want to use or in the network, say we have different bandwidth, or in the street we have different width of the street of Ho Chi Minh City, and we want to find out if we want what will be the maximum capacities of our network from one place to another. So we run this maximum flow algorithms to find out what would be the best. It means what would be the the maximum route with maximum capacities from one place to another using our network. So that will have us to find out the bottleneck. Okay. And min cut is just a thing that related to that one, to find out which is the link in our network that have the smallest capacities. And if we cut that link, that will break the network, so we cannot go from one place to another. So it means that will be the bottleneck for our network. So the maximum max flow min cut is cut application. So we have, and then we have another problem, the bipartite graph. It means the graph we have the set of, we have two separate sets, let's say male and female. They have some different criteria to select girlfriend and boyfriend. We want to find out a match couple for the two sets. So bipartite graph, we have us to identify, we have algorithms to have us to find out how to link the matching. So we call it maximum matching using bipartite graph. So finally we can find out all of the thing. So that will be some advanced a bit, but I will send you the slide, and of course you can always check in internet if you are interested in the graph theory. Actually, graph theory is a research area quite like a long, quite major now. It means we have many problems and people can use it to solve many real life example or real life problem. Normally when people do research, like it's quite traditional, but people still working on graphs. They have many different problems that people can solve, and it can apply it to many different contexts. So graph is a powerful tool to solve problems. Of course, recently people are not talking about graph a lot, but because we have rising trend is AI, machine learning and thing, but graph theory always the one of the powerful tools. Okay. Okay, so that will be the end for the graph theory. Now I will try to summarize some content and go through all the things that we can have, and we may preview for the final exam. Okay. My sample question will be review, learn everything. But here what we have. Okay, so that way the last section. This is the last section of data structure and algorithms. I hope that you may find some interesting tool, and you know a bit more on the on a different data structure. And of course, recently we have a lot new data structure. That would be the key thing that for developers and people should know in order to optimize things or to make better decision. Of course, they're a bit different from what you have a job like web developers or many software engineer. Sometimes you just work with library and tool to use to organize, do things. But data structure may have you to optimize the problem, the solution, make when your system reach a limit, so people cannot solve it. You cannot serve a lot of people, so we can increase. You can use cloud computing, but graph theory and data structure can help you to improve the code by sample code. You if to optimize it, that already improve the performance of your system. Okay, so normally for developers, you need to know it on this one. And for the interview for developers, they always ask question about data structure, okay, and algorithms. So here in our work, we have basic data structure. This is for maybe this slide, recursion, sorting. This is for before midterm, and for the final exam we will start again from advanced sorting. So that that may include quick sorts. Okay, and so we have sorting, we have binary tree, we have hash table, and then we have graph and advanced graph algorithms. It's been different kind of graph. And most of the time I will have exercise or question for all of these topics. Sorting, binary tree, hash table, graph, presentation of the graph in memory, graph algorithm, sorted bars, strongly connected component, BFS, DFS, and things like that. So that will be the exam, this part. Everyone, do you have any question related to this topic? You can always ask me. Okay. Now. Okay, for blackboard I will do it now. Yeah, I can make it multiple estimation. Final project reports. I now editing it so that you can submission detail. Okay, I changed it to unlimited submission already. So there, I have this kind of question a bit before. So please, this kind of thing is not correct because your Google Calendar or your email calendar is not set to GMT +7 as Vietnamese time zone. So that result in that kind of thing. Okay. Any focus on a topic? The focus, I think, I don't know. I will spread on anything, but of course we had question on graph for sure. We had question on binary tree and hash table and sorting, quick sort. I don't know. It may be like that. I don't know how to focus. Seven. For the final exam, yeah, let's say we have this one from this to this. At least it means at least we have 5 questions at least. The others question. No. I really want you to use Word for the exam because it's easier for us to keep track, to manage. The yeah, lighter, smaller size. So you can submit the work file. Yeah. I not decided yet, but yeah, for the final exam, we may ask you to do it in a work file or text file or whatever. But I don't know if you need some drawing, maybe you can use a paper, but I try to see how can we do it. Yeah, I think we will, of course we have some drawing. Full court question. Yeah, I normally would not ask you to run the whole application, but at least you have to write some function maybe. So just to like to standardize the way that we do exam. So in the exam, I will ask you to do in the work file. Okay. Then if we have any question that need to you to draw thing, you can draw it in a piece of paper, and you can use your phone, take a picture and pass it to the work file. Okay. Or if you can use some tool to draw, I don't know, draw IO or anything, you can draw it clearly and use it. Okay. So of course I will have some questions to ask you to draw graph and tree and hash table and binary tree, so all that kind of things. The others, any other question? Chapter 11. Yeah, okay. I will upload the second part of the graph algorithms now. What to say? Just 1 second. I will upload the slide right now. 1 second, wait for me, because before I forget, I will upload this slide graph second part. Graph part 2. Okay, send it. Okay, you have the graph on the blackboard already. Okay. No question. Say what do you want to ask? Okay, I didn't see your exam schedule. Yeah. So yeah, it means you have the exam every day or 2 exam a day. So how many questions we have for the final exam? Maybe at least 5. Yeah, non-stop. Okay. Okay. Yeah, I'm not the one that make that plan, but at least I can say sorry. Yeah, it's not efficient that way, I know. Hope that you can survive the exam. And now one more thing that I really hope that you can make comment, a suggestion for this course. Say for the lab, is it too easy? For the lecture, is it too hard? Or do you think that we have anything that you want to learn but we didn't have it in the course? Say you want to introduce, say I don't know, advanced data structure, or I don't know what, but heap, red, black tree, or any special data structure for machine learning, maybe. They just model time linear algebra. But or for the lab section, you say, hey, it's too easy. It's just a thing you want to have exercise on Reup, or I should move Reup to the beginning or something. Any suggestion, please? Hello, everyone. What do you say? Can final exam something, add messenger to add a message to no reply schedule. Yeah, you can say yes, no, whatever you want. If you say no, I know why. They didn't say you don't have to reply. If you want to say yes, yes, okay. But at least try to join the MS team to make sure that you can join the group. It should be. It's been okay. Okay. The easier exam. Okay. Okay, I will try to have more giveaway question, such as 2 + 2 is equal 4. Represent it using binary tree. Something. Okay. Okay. Yeah, I will try. Yeah. Yeah. Okay. Yeah. Sure. Easier. Yeah. 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 The lab, I grade some of them only. You can submit it again if you want. Hey, the others, suggestion. Otherwise, that's it. No. Yeah. I hope that you will have a successful exam for honor courses and stay safe. Okay. Yeah. Hope to see you in person next semester somewhere. Okay. Okay. Good luck, everyone. Projects, Hiếu, what do you want to say? What is the time for what? Hey, Hiếu, sorry, I'm not. Are you in my lab section? For projects in my team, in my lab section, everything is done. For Mr. Lâm and Mr. Phú, I don't know. Yeah, please ask your instructor. I don't know. Okay, everyone. Thank you. Good luck. Bye. Is it okay, Hiếu? Yeah, okay. Bye, everyone. Thanks.